Mars Climate Orbiter reached the planet roughly 170 kilometers below its planned trajectory because two ground systems gave the same number different physical meanings. At 9:04 and 52 seconds Universal Time Coordinated on September 23, 1999, the carrier signal from Mars Climate Orbiter disappeared as expected when the spacecraft passed behind Mars. The problem was what did not happen next. The signal never returned. After a 9-month flight, the spacecraft had reached the planet on a path far lower than the navigation team intended. NASA's mishap investigation concluded that the trajectory was approximately 170 kilometers below plan. A later safety summary described atmospheric entry near 57 kilometers instead of the estimated 110 kilometers. At that altitude, the orbiter was either destroyed by atmospheric stress or passed back into a heliocentric orbit. Investigators could not recover it to know which. The popular explanation is that someone mixed up metric and imperial units. That is true, but incomplete. A single conversion error reached Mars only because several layers designed to expose such mistakes did not work. The engineering payoff is not a slogan about meters. It is a lesson about interfaces, independent checks, anomaly reporting, staffing, and the difference between possessing a requirement and actually verifying it. Mars Climate Orbiter launched on December 11, 1998. It was designed to study Martian weather and climate from orbit, map atmospheric dust and water vapor, and serve as a communications relay for Mars Polar Lander and later surface missions. During cruise, its reaction wheels controlled orientation. Sunlight exerted a small but persistent pressure on the spacecraft's asymmetrical solar array, building angular momentum in those wheels. To prevent saturation, thrusters fired periodically in angular momentum desaturation events. Each firing changed the spacecraft's velocity by a tiny amount. Individually, those changes were modest. Over months, they had to be included in the orbit determination model. The spacecraft telemetry was not the problem. The failure occurred in ground software and in the exchange of process thruster data between teams. A contractor-produced program called SM_Forces calculated the impulse from the small firings and placed the result in an angular momentum desaturation file. Navigation software at the Jet Propulsion Laboratory then used that file to update the predicted trajectory. The interface specification required those impulses in Newton seconds. The file supplied pound force seconds. 1 pound force is about 4.45 newtons. Because the navigation software interpreted pound force seconds as Newton seconds, it underestimated the effect of each thruster event by that same factor. The error did not command one spectacular wrong burn. It accumulated as a series of small, mismodeled velocity changes. That detail matters. Catastrophic systems often fail not through one dramatic action but through a quiet stream of ordinary data that crosses a boundary with the wrong meaning. The written software interface specification was correct, it called for metric units. The ground application did not comply. The receiving team assumed compliance. NASA's board identified the failure to use metric units in the small forces file as the root cause. It also noted that the desaturation events occurred 10 to 14 times more often than the navigation team expected because of the solar array geometry. More frequent events meant more opportunities for the underestimated impulses to pull the predicted and actual paths apart. The spacecraft kept following commands. The model on Earth became less faithful to the spacecraft in space. The mismatch was not invisible. The Phase 2 report describes multiple file format errors and incorrect spacecraft attitude information during the first 4 months of cruise. For that period, the formal angular momentum desaturation files were not used in orbit determination. The navigation team relied on email notifications to model the events. Later, discrepancies between orbit solutions and unexpected trajectory behavior raised concerns. The investigation found inadequate communication between project elements and insufficient discipline in reporting and following up problems. Roles were not always clear. Navigation staffing and training were inadequate. The team was not fully familiar with spacecraft characteristics, and the systems engineering bridge between development, spacecraft operations, and navigation was weak. A planned fifth trajectory correction maneuver was not executed. None of these facts means that one person saw the full failure and ignored it. They mean fragments of evidence existed in different places without a process strong enough to assemble them into a decisive challenge to the model. An anomaly can be technically visible and organizationally invisible at the same time. A unit field in an interface can look trivial beside propulsion, guidance, and deep space communications. Yet the investigation found that end-to-end testing of the small forces ground software and its interface did not appear to have been accomplished with sufficient rigor. Independent verification and validation did not adequately cover the ground software. The interface control process was incomplete or insufficiently verified. Mission-critical elements were not consistently identified as such, even when their outputs directly affected the predicted flight path. There was no effective fault tree process asking how a small modeling error could propagate into orbit insertion. The project also lacked robust contingency planning for the final approach. This is the core systems lesson: correctness inside each component is not enough. The spacecraft software could be correct, the navigation algorithm could be correct, and the interface specification could be correct, while the integrated system still failed because one producer emitted a physically different quantity from the one the consumer believed it received. Integration is where assumptions become behavior. The board placed the mishap inside NASA's faster, better, cheaper era. It found that reductions in money and personnel increased risk and that project leadership did not introduce enough process discipline to compensate. The report did not claim that lower cost automatically causes failure, nor did it excuse the technical mistake. It argued that mistakes are inevitable in complex projects and that resilient processes must catch them. Here, staffing gaps, inexperience, inadequate training, unclear responsibilities, weak communication, incomplete verification, and insufficient follow-up allowed a controllable error to survive. That distinction protects the lesson from turning into blame theater. If the story ends with one developer typing the wrong unit, every other organization can imagine itself safe. If the story identifies a system that accepted inconsistent data through a mission-critical interface without an independent alarm, the lesson applies to spacecraft, medical devices, financial systems, industrial controls, and any software that turns numbers into physical actions. Units are part of the data type, even when a programming language treats them as plain decimals. The investigation's recommendations were concrete. Verify consistent units throughout spacecraft design and operations. Audit software for compliance with interface specifications. Validate the small forces models. Compare the primary navigation solution with alternate methods capable of revealing mismodeled forces. Train the navigation team on the spacecraft's design and operations. Conduct independent reviews of mission-critical events. Build fault trees and prepare real contingencies. Fully staff systems engineering and involve operations personnel early, so knowledge does not vanish during the transition from development to flight. A practical implementation would attach units to every mission-critical field, reject values that do not match the contract, and trend the difference between independent orbit solutions. It would assign an owner to each anomaly and keep it open until evidence closes it. These measures do more than say use metric. They create disagreement on purpose. A second calculation, a typed interface, an automated dimensional check, an end-to-end test, or an independent trajectory estimate can force two interpretations of the same number to collide on Earth, where the difference is recoverable. The safer design is not a perfect person. It is a process that expects a person or component to be wrong and makes the mismatch loud. Mars Climate Orbiter is remembered because the unit mismatch is instantly understandable. A pound is not a newton. But the mission was not lost merely because two measurement systems coexist. It was lost because a value crossed a boundary without carrying enough enforceable meaning, and because the organization trusted the boundary more than it tested it. The spacecraft's path changed by small amounts after each thruster firing. The model discounted those changes. The difference accumulated until Mars supplied the final, unforgiving comparison. Modern engineering can encode units in types, validate schemas, assert dimensional consistency, compare independent estimates, and monitor residuals for unexplained drift. None of those controls is glamorous. Together they turn a silent assumption into a testable contract. The orbiter did exactly what physics required. The recovery came in the processes NASA documented afterward: verify interfaces, staff systems engineering, report anomalies, test end-to-end, and maintain alternate ways to know where the vehicle really is. That is how one lost spacecraft became a durable design rule for systems that cannot afford ambiguous numbers.